Get started. Good morning, everyone. I am Dave Cederberg. I am the Outreach Coordinator for the Department of Physics and Astronomy here at Purdue, and I welcome you all to Saturday Morning Astrophysics. We have a presentation this morning. You know, when you look up at the night sky and you see all of these fantastic things, some are near, some are far, some are brighter, some are dimmer. How do we know how far they are relative to their brightness? And how do we figure out the distance? And that's what this session is about. So let's go ahead and get started. I'm going to turn it over. We have two presenters this morning, Dillon Hasenour and Tess Hoover. And Dillon and Tess are both grad students here at Purdue. They're doing research, and we can learn a little bit more about that toward the end of the session. But just going to say, Dillon, are you going to start?
Yep, I'm going to start
Okay.
off.
Okay, take it away.
All right. Hi, everyone. Good morning. Thanks for the intro, Dave. I'm Dylan. I'm a grad student at Purdue, and I live on the theory end of Astro at the moment. So I'm going to go ahead and share my screen, and we can get into a little slideshow. So can everyone see my screen? Thumbs up. Yay. Okay, I see a thumbs up. So the topic today, sorry, we're not as tactile or hands-on as going to Mars, but it's a very important question in astronomy, and it's really how far away is the night sky? So welcome to October's SMAP. Let's just say we have one image here, and I'm going to open the floor. These two little dots here, we have arrows on them. This may be a little bit of a trick question, but will anyone please jump in and try and say, which one do you think's farther away? Any guesses? Oh, I see a chat. One on the right. One on the right. Yeah, that's a good idea. It looks maybe a little dimmer to our eyes. That's a good intuition. Um, Again, it was a little bit of a trick question because these are very different objects. The one on the right, it turns out, is a Milky Way star that's in our own galaxy. It's 25,000 light years away. But the one on the left is a quasar, and this is a very bright object, and it is very far away, almost 2 billion light years away. So it's really the point here is that it's really hard to tell based off one observation exactly. Oh, looks a little smaller. That could be true too. Um, but yeah, so it's really far away. It's just really bright. So a lot of these objects, the catch is both a star and this quasar are point sources to us. So the size you see on the image, the size you see really it's determined by the instrumentation. It's not actually a resolved object. It's just this light that receives us based off our instrumentation has some characteristic size. And that's often correlated with the brightness. So a little brighter object may appear a little wider, like this star in the bottom left. They're really all point sources, though. We won't be able to make out any resolution. But yeah, so the key idea here is we want to introduce something, one at least class of object where we can get some intuition and get some quantitative measurement of how far away objects are. So first up, my section, part one, we're going to do a little demo, step through on our slideshow. So if you had a moment to print out the materials, we're going to be using this table on the left. We'll be filling it through. And at the end, we're going to use this graph to plot that data that we take. We're trying to gather, well, many of us have known that if you look at a light at some distance, and then you step away from the light, it's going to get dimmer. That's an experience we've all had. But how can we quantitatively measure that? And so this is an idea, this is a demo trying to step through and get a functional relationship for it. So step one, our little setup here that we set up last week, is we have a light source on the left that's going to be illuminating a backboard. And we're going to send it through a little screen here. We cut out a 1 by 1 centimeter square on this board. And it's going to let light through and it's just going to shape it. So it's not really affecting the light all that much. It's just going to let this 1 centimeter by 1 centimeter square pass through. And it's going to illuminate a backboard that has a centimeter by centimeter grid on it. So at the moment, we're currently quote unquote flush with our light source 10 centimeters away from this 1 by 1 centimeter aperture. So if we turn the lights off and I ask you the question, how much light is reaching our backboard, which is currently flush to that aperture. Then pull out your table, our 1 by 1 grid entry. We're at a distance of 10 centimeters. You can enter that in. And the area that's covered is there's one square covered because it's flush at the moment. And so then we're going to do a little mathematical thing. 1 over the area is what we're actually going to plot in the end. So if we add that to the table now, it's 1 over 1 is 1. So now I'm going to open the floor and we're going to take data together. This first instance, I've moved the backboard now. You can see in the image to the left, and it's a little blurry. Sorry, the image. But trust me, we illuminated a 2 by 2 square. So it's now 2 centimeters by 2 centimeters. And I'd like someone to chime in and measure the distance on this right image. So we have the ruler here you can see in the setup, and you'll have to pick an edge of which distance to measure. And we can just measure to the nearest centimeters. So this is centimeters. 10 centimeters is off to the left side. It's been cropped off, but we're near the 20 centimeter mark. So will anyone please unmute, or I'm going to start cold calling on people. Oh, chat's fine too. 18. Yeah, 18's great. So thanks, Alvina. So yes, let's measure on the left edge because that's where the light's going to be hitting. But it's really at 17.5 if we say the left edge is. So rounding up 18 is totally acceptable here. We won't be plotting in any more detail than whole centimeters. So yeah, 18 is great. And the area for that would be 2 by 2. So it's 4. And then 1 over the area. Can anyone chime in with a calculator or just do the mental math? Yeah, 1/4. Yeah, sorry. Yeah, okay. Maybe I didn't ask a good question. Yeah, 0.25 is what I was going for. We'll be getting to smaller numbers, so we're going to use decimals. My bad for not being clear. All right, next up, we've moved back a little bit to a 3 by 3. Will anyone who will chime in and give us these three measurements for us? 27. Yeah, I like that. It could be 26, 27. So on the front edge, maybe it's a little closer to 26. I like that, Hovind. The area then for a 3 by 3, 9. Yep. And 1 over the area there for 1 over 9 is going to give you 0.111111. So you can crop it off. So I'd write down 0.111 is pretty darn good. Amazing. Let's go to a 4 by 4 now. I know Luke had a mic earlier. Luke, would you unmute? Chime in?
The distance,
Yep. Distance?
almost 35.
Yep. 35. Totally great. What about the area of a 4 by 4?
16.
Yep. Do you have a calculator on hand?
Uh, I have my phone.
So 1/16 is
0.0625.
amazing. Perfect. Thank you. All right, let's get someone else in. Who else had a mic? Noah? I think, did Noah have a mic earlier? Do you mind typing? Would you give us the answers for distance, area? Yeah. Distance. Yep. 40, 45. That's good. And the area of a 5 by 5 then is 25. And for everyone that doesn't have a calculator, 1/25 is about 0.04. Thanks, Noah. All right, let's jump now to a 6 by 6. Who will jump in and help out? 53. Thank you. Yeah. 53 is great. Area 6 by 6. 36. Perfect. And 1/36. Yeah, 0.0277. Thank you. That's perfect. All right, we got two more, just two more quick. So an 8 by 8 grid, 70-ish. Yep, Hovind, I agree. Absolutely. The area is going to look like 64. Perfect, Anton. and 1 over the area. Yep, thank you for chiming in. 0.0156. All right, final one, 10 by 10. What's the distance area of a 10 by 10 and then 1 over the area? Yeah, 87. I'd probably round down to 87. 100 is the area, and 0.01 is 1 over the area. Thank you. Perfect. So now then, we filled out our data table. Thank you for everyone's help. Let's try and plot it. So I'll give you a minute now to plot some of the data points, starting on the left. So notice we're plotting on the x-axis the distance we measured, and on the y-axis we're going to plot 1 over the area. So I'll give you all a minute or two to plot. I'll scroll back up as you're all plotting. Maybe you can see. Do you see this 10 by 10 grid? We see the light. If we assume our flashlight here has been constant brightness, it's been emitting the same amount of light per time, and it's all passing through the 1 centimeter square. And we see that this light has been spreading out. And so each square at these different positions are receiving less light. So that's why I'm plotting 1 over the area, because the light per square, as if we were an observer on Earth looking at a star light years away, we would only get that tiny fraction. We'd be 1 square looking at it. So that's why we're plotting 1 over area. Great. Okay, I see we're approaching 11:20, so I'm going to go ahead and show you all, if you come back to the slideshow. This is me plotting the data that I collected. So I have my little table over here in case you missed any points along the way. And this is me plotting the data. So I'd like anyone to chime in now, either chat or unmute, and you can chime in. What kind of relationships do you see? Could you describe what's going on? So the simplest thing I could say is as we get farther away, the area is increasing. And so 1 over the area is getting smaller. Every point is getting smaller. Exponential decay? Maybe. That's a good idea. It could look maybe exponential. It is pretty rapidly declining. Anyone else? Oh, I see a couple. Okay, Hovind and Adu said. Yeah, so we could actually plot that. You said exponential decay. What if I plot these curves? So I'm going to plot 2 lines here. One of them is area over distance, and one of them is area over distance squared. So the idea here is really, so if you're saying exponential decay, functionally that would look like e to the minus x, if you've seen it in a algebra class or a math class before. What I'm plotting here is really just 1 over x or 1 over x squared, where x is our distance. So the idea of the blue curve is if you get twice as far away, you go from 10 centimeters to 20 centimeters, the light will spread out over 2 times the area. So 1 over the area is half. It goes from 1 to 0.5. And you see this curve, though, it does not fit our data at all. But the orange curve does fit pretty darn well. So, and the orange curve is the idea of 1 over distance squared, or 1 over x squared, if you've seen in math classes. And what that is saying is I get twice as far away, the area spreads out by 4 times as much area, right? We're going from a 2 by 2 to a 3 by 3. So you get 2 factors of area increasing. And so our 1 over area function is decaying pretty fast. It goes from 1 to 0.25, then from 20 centimeters to 40 centimeters to 0.125, and so forth. Amazing. Any questions here before we move on? So I want to connect this to brightness now. So our takeaway from this demo is, since the data agreed with that orange curve well, we'll say that our relationship here is 1 over the area is going by 1 over distance squared. And now let's connect this to actually how much light each square is receiving. I said this a bit earlier, but if we assume that all the light passing through our aperture, our little 1 by 1 centimeter square, it's the same amount of light each moment, then as we've done this setup, you can see that the squares are getting less light because it's spreading out equally across this area. So I included our little, 10 by 10 grid. And you can see each square is receiving about the same amount of light, minus the one square there that has like a glare. There's something in the photo, a glare or a reflection that's a little brighter, but everything else is pretty equal area. So that tells us each square is receiving like 1 over the area amount of light. And in astronomy, we'll give that the name flux and we'll call it with a capital F. So really what we're saying here is our light received is going by 1 over the distance squared. And this is what we call an inverse square law. Inverse because it's 1 over, square because it's distance squared. So the key takeaway here is that our flux, the amount of light we're receiving from an object, goes by 1 over distance squared. So if we could see an object, have an idea of how bright it is, how bright it appears to us, we can get an idea of how far away it is using this relationship. Any questions before I hand it off to Tess? So flux is defined as the area light covers. Kind of. Yes, that's a great intuition. If you want the formal definition of flux, it's the light per square per second or per moment per time. So every moment in time, this square is receiving some amount of light, and it's that amount of light per the area of your square. And so since we set it up as 1 centimeter by 1 centimeter squares, we'll get per centimeter squared is a unit. Does that answer your question, Adu? So now I think it's time to hand it over to Tess, and I'll let Tess share screen and control the PowerPoint.
Okay. Hello, everybody. So my name is Tess Hoover. I am also a grad student here at Purdue, and I also work on supernovae, which is what I will be talking to you about. So what I'll be telling you is from our eyes to mouth. We talked about flux, and we talked about how much light gets to us. But the thing is, our eyeballs don't see in flux. Astronomy is a really old field. We started with people just looking at the sky. We didn't have fancy cameras that could count, how much light actually reaches us. And so we have to honor history and we have to keep going with that. And so that means that there's a couple funny things that have to happen. So first off is that our eyeballs see in what's called log scale, which is pretty much we need to reframe flux in this log language because our eyes actually see in this log language. And so that's the first thing. The second thing is also because history is funny, we end up with this negative sign. And what this negative sign tells us is that more negative or smaller numbers are brighter. So those are the two things that happen here. And so we have these two different types of things. Well, okay, so we put it into log scale, and that actually tells us the brightness, and we call this the magnitude system. So we have two types. We have apparent magnitude, which is if I look at the sky, how bright does it look to my eyeball? And then we have absolute magnitude, which is a standard way to say this is the actual brightness of this object if I were to stand next to it. Because we know that that brightness changes, we can't just say that the brightness we see is actually the brightness of the object, because we know that brightness changes with distance. And so we have to define apparent magnitude, which is what your eyeballs see, and absolute magnitude, which is how bright the object actually is. And if we know both of these, we can use this thing called distance modulus, which spits out a distance. So we can say this is how bright we see it. We say this is how bright we know it is, and this is how far away it is. And we have this really nice relationship. This is pretty much just saying your flux relationship, but in a different language. Right, so that's the first part. Now we're going to do a fun little activity. I want you guys to vote. So based on how bright, I'm going to put the chat open so you guys can vote. How bright our eyeballs see these stars?
Are we voting for how they appear or how they actually are, or both right now?
We're going to vote on just how they appear. So if you're just going to look at both of these stars, which one are you going to see is brighter? Yeah, Betelgeuse. And how bright does your eyes see Betelgeuse as? If we were to give that a number. 0.5. Brilliant. And so now, if we were instead to say, okay, which star is actually brighter though? So not how bright does it look to us, but which star is actually brighter because that star itself is brighter.
Oh, wow. I just saw your question. So we're kind of comparing the numbers on the table too. So the first row of the table is how much it appears, and the bottom row is its intrinsic brightness, measured at some distance.
Okay, it looks like everyone voted Polaris. So,
Oh, we got
oh,
to go.
Alvina said Betelgeuse. Okay. The answer is still Betelgeuse, actually. So the more negative number is bright. So we know that Betelgeuse was brighter to our eyes because it was a smaller number, but the more negative number is going to be the brighter one too. So it's actually still Betelgeuse. Betelgeuse looks really bright to us, and Betelgeuse is just really bright. And now I'm going to tell you about my favorite objects right now, type 1a supernova. Who can tell me what a supernova is? Yeah, when the star size. So some stars, when they get to the end of their lifetime, they just explode. Some stars, at the end of their lives, they explode. And so some of those stars, when they explode, they go off in what we call a type 1a supernova. Type 1a is a very special type of supernova, and it's so special that it allows us to do really cool things as far as distance measurements. Type 1a supernovae are something that we call a standard candle. I'm not going to go super into that. I did add a little bit of info on that in your worksheets. If you do want to read it, go ahead. It's pretty cool. Pretty much what it means is we know how bright they are given some more information. What we know is they all have this kind of shape. So this is the amount of time. We know that they have their peak at 0, and then these are more days, and we keep taking data and we see how bright it is. That's their luminosity. And we see how bright it is at each day after it explodes. And so we can tell that these really, really bright ones have these really wide light curves. And these not so bright ones, these dimmer ones, have really steep light curves. And so there's a relationship between how bright it is and how fat it's squished out to be. And so we can relate the brightness and the width, how fat your light curve is, and we can scale them all to look identical. And because they have this really, really cool property, we can always tell how bright it is if we know how wide it is. And that is what we'll be using in our activity today. So you have to know this. Oh, so this is another one of those light curves. This is from a supernova called Supernova 2023 EHL. That's not super important, but just if you wanted to Google it. And so this is the light curve that you will be doing your activity on. And as you can tell, this is your brightness. This is how many days you have. And notice we care about this B band. That will be important later. So when you're looking at this data, you want this blue curve. And that's what you'll be using to do your activity. And you can tell from here, like it's very wide, right? So maybe this thing is really bright and it's kind of wide and stretched out. And that's something to look at. And so because we can say, oh, this is kind of wide, we can use what we call the Phillips relation. Now, I know there's a lot going on here. I'll walk you through it. Don't be scared. We have this thing called delta M15. Can anyone tell me what delta means? Do you have an idea of what delta might mean here? Yeah, delta is the change. So M, we talked about M. What does M mean? Magnitude. Absolute magnitude or apparent magnitude? We talked about two different magnitudes. Yeah, it's little m, so it's apparent magnitude. Apparent magnitude is what we measured on our light curve. This 15, does anyone have an idea of what this 15 might mean? The days, there we go. Good job. Yeah, so we're looking at the change in the apparent magnitude over 15 days. This B is because we need to look in that B band, so that blue data that I was showing you. and we're going to look at how the brightness changes over 15 days. Each of these little crosses is actually a supernova. These are actual supernova measurements, and they all kind of lie along this way. And so if you put a curve there, you know, hey, my supernovae all look like they follow this curve. And based on that, if you know your delta M15, you can follow it up to the curve. And then you can say, wait, it matches whatever value over here. Does anyone want to take a guess of what this number means? Absolute magnitude. Yes, we have a big M. So little m's are apparent. Big M's are absolute. Yes, yes, the real magnitude. And so based on this, we can see how bright it actually is. And if you remember from your distance modulus, if we know how bright we see it, and we know how bright it actually is, we can tell how far away it is. So that's what you'll be doing in your activity. You'll be using that light curve to figure out how far away this supernova is.
And we're going to go to breakout rooms next, I think.
Let's see. Let me pull up my screen. Can anyone unmute and read the first step here and what we want to do to figuring out the distance? That's what we're doing. We're figuring out the distance to the supernova.
Sure. Locate the peak of your light curve, both the time and magnitude, and
Mhm.
find 15 days after the peak and find the new corresponding magnitude.
Yeah, exactly. So if we go down here, how would we find, remember, we're looking at the blue band. So this blue curve here, and that's just because all of these are offset by specific values to make the graph easier to look at. If it wasn't offset, these would be overlapping. And so the blue one is the only one that is not offset, so it's just easiest for us to look at right here.
Do people understand like the difference between the colors, like why we have different colors? The different colors are different bands of light, but basically the blue is a specific range of light we're looking at, and astronomers care a lot about it. It's not super important now, but just so you don't get confused with the colors, they're basically telling a very similar idea, but we're just focusing on blue.
All right, so we're looking for the magnitude. Remember, this is apparent magnitude that we're looking at here, as Tess discussed. So we want to find the peak brightness. So that means at 0 days. What is the magnitude here for this blue band on this dotted line? It may help if you have a ruler of some sort to kind of line it up horizontally and draw a line over to this y-axis here.
1.2.
Perfect. Yes, 1.2. So that is our delta M15. It's a scary name. It's a really simple concept. We just go 15 days later and see what the difference in the magnitude was. So, and it's really useful. So that is our delta M15. Perfect. Let's go back now to the Phillips relation. Let's take this measurement, go up. So we've hit the Phillips relation. This thick black line is our fit of all our observational data. We've gone up from 1.2, and now this tells us what? Will anyone chime in? So the number capital M is going to be minus 19.3. That's where it intersects this y-axis. But what does this mean again? Can anyone remind us? Absolute magnitude. Yes. And specifically, this is the absolute magnitude at peak. So we have its absolute magnitude at peak. And if we scroll back up to where we measured this, we have its apparent magnitude at peak. We have 15.4 is its apparent magnitude at peak. And now we have a measure, we have an idea of its intrinsic, its absolute magnitude at peak. So this is where the scary distance modulus comes in. So this is in the form we often see if you open up an astronomy textbook or if you see it in a paper, etc. The distance modulus is going to be the difference in your apparent magnitude and your absolute magnitude, and then a function around distance. So if you're not familiar with the logarithm, that's totally okay. You may not have reached it in classes yet. So we went ahead and rearranged it and solved D for you. So D is 10 to some power. So it's going to be 10 to some power, and we're going to call that A. And A has just been rearranged to be 1/5 of m minus m plus 5. So now I want someone to chime in. This is a little equation for you. So we have our peak apparent magnitude. We measured as 15.4. And from the Phillips relation, we have its absolute magnitude to be minus 19.3. So what is A? You may need a calculator for this one if you don't want to divide by 5. 7.94. Sam's nodding his head. Yeah, those are great, Hoven, Alvina. Absolutely great. Yes, 7.94. So is that a consensus for our breakout room? I think we're going to come back all together as breakout rooms and say our measurement there. So 7.94 is what we got.
I did have one question. Go back to the equations that we're doing.
Mm-hmm.
The distance, okay, right there. The m minus m plus 5. Where does that 5 come from?
Why fives are appearing?
Yeah.
So yeah. No, this is a great question. We've been using absolute magnitude, and I said it's intrinsic brightness, but that's with respect to some distance. I have to stand some distance away from our light. And in astronomy, we made a historical choice to say 10 parsecs, which is like 30-ish light years, I think. So we chose if we were 30 light years or 10 parsecs away from our object, how bright would it be? That's our characteristic thing. And since we chose that distance, that's where these fives come from, is the unit of parsec, basically.
Also, Dylan, just really quick, it looks like we do have a question in the chat. Alvin asked, why do we measure the brightness at 15 days?
Oh, that's a great question, Alvina. I love these questions. Okay. So let's go back up to our light curve. Alvina. Okay. So you can see this light curve. No, actually, I'm going to scroll back up a bit further. So this is a lot of type 1a supernovae, right? What you can see is after peak, there's kind of two different rates that we see. So there's this rate, it's declining quickly, and then it kind of turns off and declines more shallowly, more on a more shallow curve. This is very related to what we think is going on in the supernova, which is a lot of nuclear fusion has just occurred. We've created these radioactive isotopes, a lot of nickel 56, which is radioactive, and it will decay and release energy. And that's the light that we see is from the radioactive decay of nickel 56. And so that happens early on. It's about a half-life of 7 days. So half of your nickel will have decayed at 7 days. And after this, the slower turnoff is the decay of that byproduct. I think nickel goes to cobalt, if I remember correctly. So it's cobalt decaying. Wait, is that right? Is it cobalt? I don't know. I don't have the periodic table open. But whatever isotope it decays to, it's also radioactive, will decay on a longer time scale. So that's the light we're seeing. And that's related to these two slopes. So 15 days is chosen because it's related to that half-life of nickel-ish, where we want this first part of the slope. So we want it before it becomes shallow. And it's
Okay, so everyone got around 7.9. When I did this, I'm pretty sure I got 8.2. So that is the value that is on the slides. And that is the value I'm going to be using for the rest of this presentation. So pretty much we have this A value, and then that is the exponent on some 10. Oh, 8.9 is pretty high. I would be suspicious of that. You might have a negative sign missing or something funny. Some funny business. And so we put that on a 10 to get our distance. We fill in those blanks. I used 8.2, but based on that, if you plug that in here, you get 8.2. This is in terms of parsecs. Parsecs are just a really big unit of distance that's pretty standard across astronomy. But if you want to think of that in terms of light years, this is really, really far away. The light from the supernova took 520, that's million, years to reach us. It's so far away. But so still, they're so bright that even if they're so far away, we can still see them and still do brilliant science with them. And that's why I love them. They're so cool. Okay, so now we know how far away it is. So now I'm going to show you some pretty
Quick
pictures.
question, Tess. PC
Oh,
it is a unit. It's called parsecs. It's a different historically motivated thing, but if I remember, it's roughly 3 light years. So they're both units of
yeah.
distance, just defined for in slightly different ways. It was defined based off Earth's rotation around the sun and some characteristic angles. But a parsec, I know you hear, maybe you heard it in Star Wars. It is a unit
We don't
of
talk about that.
distance, not time. To be clear, it's called parsec, but it is distance. So, yes.
Okay, dokes. So I'm going to show you some really cool little supernovae that I found just Googling. So this is, you can see it right here. Oh no, it's not. Is it working? Okay, it's flashing. So this is a galaxy that is really far away. This is the M74 galaxy. And you can see the supernova going off in it. It's so bright that it's as bright as our galaxy. But do note, this is a type 2 supernova. I told you type 1As are the super special kind that we can use to measure distance. This is really bright. We can see it. It's very dramatic. We cannot use it to tell a distance to this galaxy. Here's another one. You can see the supernova going off right here. This is in the galaxy NGC 7331. And you can see that the supernova goes off. It's very bright. It's as bright as a bunch of these foreground stars. And it lights up the whole galaxy. It makes the rest of the galaxy look dim by comparison. But again, this is a type 2 supernova. So as pretty as it is, we cannot use it to tell the distance to this galaxy. Finally, I'm going to show you my favorite supernova image. We have this brilliant supernova going off right here. This galaxy is NGC 4526. This one's not a cute little GIF, that's why I put it last. But this one is a type 1A supernova, which means based on seeing this supernova, we can measure the distance to this galaxy. And so now not only do we know how far away the supernova is, we know how far away the galaxy that supernova lives in is. And this is part of why they're so powerful.
Type 1A, maybe just inward.
Yeah, I wasn't going to get into that.
Yeah. Well, we shouldn't get into it, but there's a minute. There's a minute left. We think of them
I
as
just wanted to show you guys how powerful this of a tool a type 1A supernova is. That's the idea here. If we want to get into more supernova talk, we can. I'm always down. But like the takeaway I need you to get from this is that type 2 supernovae are very, very cool in their own right. Type 1A supernovae have this extra special property that allows us to do very powerful things in astronomy. That's the big idea.
Oh, we got to show our thank you
Thanks for
slide.
listening.
My cat and Tess's cat.
Tess,
We need cat representation.
Tess, I have a question. So I'm
Yes.
thinking of the light curve that you showed that we use for our calculation and the images that you just showed. And I see the supernova turning on and then it will fade. And I go back to the light curve and I know they fade significantly in the first 15 days. But what's the lifespan? How long are we talking that they will be visible for? 6 months or a year, or how long do they last typically?
This is actually something we talked about a little bit in our breakout room. Like, what happens to these? Do they just disappear? And the answer to that is they get dimmer. They get much dimmer. As you can see, like it does get much dimmer. The ability of how long you can actually look at them for is how dim can you see things, which is why people are making very, very powerful telescopes so that we can see them for longer as they get dimmer. But one of the questions we got was actually, more interesting than how long can we see it, because how long we can see it is pretty much how good is your telescope. But like what happens to it? It's not just going to be glowing in the sky forever. But what happens is like the star exploded. It shot its guts into space. Its guts aren't just going to disappear. So what ends up happening, and Akshay pulled this up, so I will also pull this up because it is beautiful. We get supernova remnants. And so these are all supernovae that went off hundreds to thousands of years ago, and we can still see their guts. And so you have different types of supernova. So this is the Crab Nebula. It's very cool. But you can see you have all these structures of how those guts got shot out. Or this one is Tycho. Tycho is one of our Type 1As. And so you can see the structure of the guts that got shot out of Tycho. These things are hundreds to thousands of years old. And you can still look at them and you can still do good science so long as you have the telescopes to be able to look. And they're absolutely beautiful. Like this is I don't know this one. That's the crab again. Here's another supernova remnant. Tycho again. This is Cassiopeia. Everyone loves Cassiopeia. And you end up with all these very beautiful structures of these supernovae that went off so long ago that we would never, we can't study their light curves, but we can still study them. And it's very, very cool.
This isn't from the breakout room, but this is a question that I think would be interesting to answer. So you said that type 2 supernovae we are not able to use them as this measure of distance. Would you be able to briefly explain why that is and why these type 1As are so unique to us?
Yeah. So type 1As have that light curve, that measure of squish where we can make them all look the same. And type 1As have that property. Type 2s just don't. Type 2s have a lot more variation, which means we can't standardize them. It means we can test like other great physics with them to see like, oh, this is the situation that was here, and this is what that ends up looking like once it explodes. You can get great physics out of that, but it's different physics. Type 1As are very consistent. And because they're consistent, we can scale them. And because we can scale them, we can use them to measure distances.
Students here. So thank you for your presentation. Thank you for the TAs. And thank you for all of you students who have participated with us. I put a link in the chat that will steer you to one of our other Saturday morning astro sessions on the YouTube channel. It's about type 1A supernovae, and it is about how we colorize, how astrophysicists and astronomers colorize the supernovae. They start with black and white images and end up with these beautiful color images that you just saw. We explain how they do that. And in fact, you can do it too. Check out the video in your spare time and have some fun and let us know if you have any questions.